Hello everybody, I am Mr. Mushabadi and welcome to another Solving Math 1110 GYI tutorial. So today we're going to be looking at rational and irrational numbers. So without wasting much of your time, let's get into it. Hey, so today we want to know what exactly rational and irrational numbers are. So we're going to start first with rational numbers, then we're going to move on to irrational numbers. All right, so let's start with rational numbers. What are rational numbers? So rational numbers are numbers that can be expressed in the form m over n, where m and n are integers and n is not equal to 0. All right, so basically rational numbers are more of a fraction, and the numerator is not supposed to equate 0. So this is what this means. And another thing that you need to take note of about rational numbers is that their decimal expansion can either terminate or repeat itself. All right, so when we say it can either terminate or repeat itself, we have examples here showing that. So we can see that 2.14 does not continue, it just ends up to 4. So it just terminates, the decimal expansion just terminates. And here we can see that 3.3131, it repeats, this decimal expansion here repeats. So any number that you see that has a decimal expansion that terminates or repeats itself is a rational number. Okay, so to just explain further on rational numbers, we have an example here. All right, which says show that 0.71 is a rational number. So I'm pretty sure most of you are wondering what this block here means on top of 71. This block just simply means that 71 is recurring, or rather it's repeating. So I'm going to illustrate further as we start solving this example right now. So I'm going to use my green marker here, just differentiate the two. So we're going to say x is equals to 0.71 with the bar on top. So to just illustrate what the bar means, so we're going to say x is equals to 0.7171. All right, it just means that 71 is recurring, so we can continue writing 71, but yeah, we're just going to end here. So the next step here is to multiply 100 with both sides. So the reason why we're multiplying both sides with 100 is because there are two decimal places here, so we need to take the repeating side to the other side. So what we're going to do is we're going to multiply 100 with both sides in order for us to get the 71 to the other side. So we're going to say 100 times x, so we're going to have 100x here, and we're going to have 7171. All right, so the next step here is we need to subtract x from 100x, and we need to subtract 0.7171 from 71.7171. I know that sounds confusing, but yeah. So to do that, we're going to say 100x minus x is equals to 71.7171 minus 0.7171. All right, so to multiply 100x x from 100x, we're going to have 99x. All right, then to multipy this from that, or to subtract this from that, we are going to have 0 here. So this is just going to give us 0, a point there. Then 1 minus 0 is just 1, and 7 minus 0 is just 71. All right, so our expression here says we have 99x equals 71. So we need to make x the subject of the formula. So we're going to divide everything by 99. We're going to cancel that. Then we're going to have x is equals to 71 over 99. And that's our final answer. So we need to take note of the final answer here. We need to ensure that the final answer is always in its simplest form. Okay, so for this one, we can just leave it here because this is the simplest form. There's no number that can go into 71 and 99. But if you feel you want to continue, you can continue it and stuff. So since we're not using a calculator in this course, so we can just leave it here. All right, and then so we can see that our final answer shows what we talked about in the definition of what a rational number is. We said rational numbers can be expressed in the form m over n, and n is not equal to 0. All right, so we can see here that our final answer is 71 over 99, which is just m over n, and the denominator is not equated to 0. So we can see that this here is a rational number. So this is how we show that 0.71 is a rational number. So that's it for this example. We can move on to the next one. Our second example here says that show that 4.83 with the bar on top there is a rational number. Okay, so we're going to do this the same way we did the previous one, although a few things are going to be different here. You're going to see anyway as we move further. So we're going to say x is equals to 4.83 with the bar on top there. Then we're going to say x is equals to 4.8333. So 3 is the recurring number or the repeating number. Then we're going to multiply both sides with 10 because we want to get this number that is not repeating to the other side. So to do that, we're going to say 10x is equals to 48.333. All right. So the next step is for us to also get the repeating block to the other side. Okay, so the only repeating block here is 3, so it's just 1 decimal point. So we're going to multiply both sides with 10 again because it's just 1 decimal point. All right, so but if it was 3131, to get the 31, we need to multiply both sides with 100. So in this case, it's just 1 decimal point, so we're going to multiply both sides with 10. So 10 times 10 there, we're going to have 100x. Okay, then 10 times that, we're going to have 483.333. Good. Okay, so now we need to subtract 10x from 100x and this from that. Okay, so we're going to say 100x, and in this case, just ignore the x here. So in this case, we're just dealing with the 2. All right, so we're going to have 100x minus 10x, and we're going to say 483.333 minus 48.333. Okay, so we're going to have 0 here, 0 here, 0 here. All right, then we're going to say 13 minus 8, which is going to be 5. Then we're going to say 7 minus 4. We carried 1 here, so just in case you're confused. So we're going to have 7. 7 minus 4, we're going to have 3. Okay, and then 4 minus 0 is just going to be 4. So we have 435 there, and we have 10x, 100x minus 10x. So we're going to have 90x on this side. Okay, so in order for us to make x the subject of the formula, we're going to divide everything by 90 over 90. Okay, so we're going to have x is equals to, so we need to find a number that can go into both this number and that number. So we can start by saying, let's try 3. Okay, so 3 into that, we are going to have 1, carry 1 there, 3 into 13, we're going to have 4, then remainder 1, so we're going to have 15 there, then 3 into 15, we're going to have 5. All right, then on the bottom side, 3 into 90, we're just going to have 30. Okay, so to simplify this further, we're going to say, we might use 5 here because 5 can go into both. So 5 into 145. So we can say, for those that want to understand better, so we can say 5 into 14. We can say 2, remainder 4. Okay, then 5 into 45, we have 9. So we have 29 on top there. Then 5 into 30 is just simply 6. So that's our final answer. So 29 over 6 is our final answer, because, and we have expressed this in the simplest form. And we can see that 6 here is not equal to 0. So we can see that our final answer is a rational number. All right, so let's move on to the next thing, which is knowing what exactly irrational numbers are. All right, so now we want to know what exactly irrational numbers are. What are irrational numbers? Simple. Irrational numbers are numbers whose decimal expansion is either non-terminating or non-recurring. So which means that it does not terminate or it does not repeat. Okay, so we have examples here of what irrational numbers are. So the square root of 2 is equals to 1.4142135562. Okay, so we can see from this expression here that it's non-terminating, it keeps going, and it's also not repeating. The expression is not repeating. So we have 414213. There's no number here that is repeating. And from square root of 3, we can see that it's the same thing that's happening. We have 1.7320508808, and we can also see that this expression right here is non-terminating and also non-recurring because it keeps on going. All right, so an important thing that we need to take note of about square roots is that the square root of a perfect square is a rational number. So what we mean is that a perfect number is something like 9, 16. Yeah, so we can see that the square root of 9 is equals to 3. So this is just, we can refer to this as a rational number. Okay, so don't get them confused. All right, so we're going to move on to an example just to give us a full understanding of what exactly irrational numbers are. So our example here says that prove that the square root of 2 is a rational number. So in order for us to prove that the square root of 2 is a rational number, we have to make an assumption. So we're going to assume square root of 2 is rational. Okay, and since we're assuming that, and since that we're assuming that the square root of 2 is rational, we're going to say then the square root of 2 is equals to the expression m over n. Okay, so since we know what a rational number is any number that is expressed in the form n over n. So we need to equate it to this in order for us to to match it with what we are trying to assume here. Okay, so the next thing we're going to say is that m and n are integers. Okay, m and n are integers, and n is not equal to 0. Okay, so m and n should be expressed in their lowest terms. At the same time, m and n should have no common factors. So this is everything that you need to include in your solution when you're trying to prove that square root is a rational number. So the next thing, now we're going to get our expression here, and we're going to say n, the square root of 2 is equals to n over n. And then in order for us to get rid of the square root, we're going to multiply everything with the power 2 here, both sides with the power 2. So we're going to multiply there, and we're just going to have a 2 here, and then we're going to multiply the power here with everything inside. We're going to have m squared and n squared. Okay, so we need to have okay, so I'm going to write our expression here, our current expression. So we have 2 is equals to m squared over n squared. We need to make one of these elements or variables the subject of the formula. So we're going to cross multiply, then we're going to have m squared is equals to 2n squared. Okay, now that we have that, so this is our final expression as at now. So from this expression, what can we get from it? So we can see that m squared, we can see if we're trying to make n squared the subject of a formula, we're going to divide everything by 2. So if we're dividing m squared by 2, we can see that m squared is a multiple of 2. So m squared is a multiple of 2 because it is divisible by 2. Okay? Another thing that we can get from this expression here is that since m squared is divisible by 2, sorry about that, is divisible by 2, then m itself, not m squared, but m itself is also divisible by 2. Okay, so we can see that here. So what our expression here simply tells us is that m squared is a multiple of 2 because it is divisible by 2, and since m squared is divisible by 2, then m itself, sorry, so I hope you can see that, so I almost wrote m squared here, so m itself is also divisible by 2. Okay, so in this case now, we're going to say, in order for us to show what exactly is going on here, when we say m itself is also divisible by 2, we're going to say m is equals to 2k for some integer k. Okay, so my marker is fading out, so I'm just going to use the red marker instead. So we're going to say m is equals to 2k for some integer k. So the reason why we have this expression is just to show what exactly we mean when you say m itself is also divisible by 2. So if we're going to make k the subject of the formula, we're going to divide by 2, and we can see that m is also divisible by 2. So that's what we're trying to show here. And now, because we're trying to show that here, we're going to go back to our original expression here, which is m squared. Okay, so let me do that. We'll move that up, which is m squared is equals to 2n squared. Okay, so we're going to substitute m with this 2k here. Okay, so we're going to say 2k to the power 2, the 2 here, is equals to 2n to the power 2. Okay, let me just write our expression here. So 2k to the power 2 is equals to 2n squared. All right. So now in this case, now we're going to simplify this. Sorry, this has to be in brackets. So we're going to multiply the power with everything inside. So we're going to have 4 here, k squared, and equals to 2n squared. Okay, so now we're going to make n the subject of the formula. We're going to divide everything by 2. So we're going to have n squared is equals to 2k squared. I don't know if you can see anything that's common here with our former expression here. So we can see that 2n squared equals 2k squared is almost similar to m squared equals 2n squared. So what we can get from this is that n squared is a multiple of 2. Because it is divisible by 2. Okay, another thing we can get from here is that since n squared is divisible by 2, then n itself is also divisible by 2. So we're going to say since n squared is divisible by 2, then n itself is also divisible by 2. Okay, so now we're going to analyze both expressions here. So what can we get from both expressions? So we can see that both m and n are what? Are divisible by 2 because are multiples of 2 because they're divisible by 2. And then we can see that n squared is also divisible by 2. Since n squared is also divisible by 2, then n itself is divisible by 2. And here we have m squared. Since m squared is divisible by 2, then m itself is also divisible by 2. Okay, what this simply means is that there's a contradiction between the two statements here. Okay, and the contradiction comes back to what we said here. We say that m and n should have no common factors. I hope you understand that m and n should have no common factors. Both m and n are multiples of 2, and both n and m, okay, are divisible by 2. Okay, so we can see that that's a common factor there. So we can see that this expression here is contradicting the fact that m and n should have no common factors. So we can say that. This statement is contradicting. This contradicts the fact that m and n have no common factors. Okay, which implies that the expression square root of 2 is equals to m over n is not rational. Okay, so we can see that this expression here is an irrational expression, and it cannot be rational. So we can see that square root of 2 equals to this is something that is impossible, because these two have a contradicting fact, which is m and n have no common factors. So we can see that the expression here is not rational. So this is how we can answer a question like this. Whenever you're given a question like this in an exam. I know the process is quite long, but you have to ensure that you illustrate everything, because you're proving in this case, so you need to show everything that we've done. So we moved from that, we came down to this, and now we came down to this. So this contradicts the fact that m and n have no common factors. Hence, the square root of 2 equals m over n is not rational. All right, so our last example here shows that says that show that 3 plus the square root of 2 is a rational number, given that the square root of 2 is irrational. Okay, so it says show that 3 plus the square root of 2 is a rational number, given that the square root of 2 is irrational. Okay, so just like the previous example, what we're going to do here is we're going to assume, so we're going to assume that 3 plus the square root of 2 is rational. Okay, all right, after assuming that, then since we're assuming that this is rational, then this expression here, 3 plus the square root of 2, should be equals to, in the previous one we're using m over n. In this case we can use a over b, and b should not equate to 0. Okay, all right, so now we're going to get our full expression here, which is 3 plus square root of 2 is equals to a over b. So in this case, we need to take the 3 to the other side. So we're going to have square root of 2 equals a over b minus 3. Okay, so we can just say 3 over 1 here. 1 is our denominator. So in this case, we need to simplify this. So to simplify this, we're going to make b our denominator there. Common denominator. So we're going to say b into b, we just have 1. So we're going to have, let me just say square root of 2 equals, so b into b is 1. So we're going to have a, then 1 into b is b, minus, then b times negative 3, we're going to have negative 3b. All right. So in this case, we can see that the square root of 2, okay, the square root of 2 is equals to a minus 3b and b. So this is our final answer here. But what exactly does this expression, which is our final answer, tell us? So I'm going to write down our expression here on the other side, on this paper here, so we can just see what's going on clearly. So we're going to say square root of 2 is equals to a minus 3b over b. All right, so what we can see from this expression is that we can see that the right hand side is rational and the left hand side is irrational. So we can write that down. So right hand side, you can write this in full. I'm just going to write this in a shortcut form. Right hand side is rational and left hand side is irrational. Okay, so we can see that the right hand side is rational and the left hand side is irrational. Okay, so this simply tells us that there's a contradiction here, because there's no number that can have both irrational, can have both irrational, can be both irrational and rational. Okay, so this is a contradiction. So we can say this is a contradiction because there is no number that is both rational and irrational. Yeah, so this contradiction just says that there's no number that is both rational and irrational. That's what the contradiction is here. And so since this contradiction proves that there's no number that has both rational and that can be both rational and irrational, so we can say hence 3 plus the square root of 2 is not rational. All right, so this concludes our solution for this question. Okay, so we've just proved that this expression, the expression that we were given in the question, cannot be rational. All right, so because our question says show that 3 plus the square root of 2 is a rational number, given that the square root of 2 is irrational. But a number cannot be both irrational and rational at the same time. Hence, the expression 3 plus the square root of 2 is not rational. So that is the final answer for this question. Just in case you're asked to show or prove in an exam, you can do exactly what I've done here in this tutorial right now. So last point that I want to make out is that rational numbers. Okay, so rational numbers can be denoted. So rational numbers can be denoted by the symbol Q, and irrational numbers can be denoted by this. So anytime you're asked to denote what a rational number and irrational numbers, so a rational number can be denoted by this, which is just a Q, and irrational numbers can be denoted by this, which is IRR. So we can say, so to just prove this and just to explain this further, so if if we want to intersect rational numbers and irrational numbers, what do we get? So we have irrational numbers intersection this, we're going to have what? A null set, or rather an empty set. Okay, because the set, the Venn diagram or the universal set of irrational numbers and rational numbers is a disjoint set. Okay, so to just show that, we can do that. So we can say irrational numbers on this side and rational numbers on the other side. So we can see that it's a disjoint set. Okay, so but what if we were to unite this? What would we get? So if we unite irrational numbers with rational numbers, we're going to get what? This, a set of real numbers. Okay, so what you get when you unite irrational numbers and rational numbers is what? Is real numbers. You get real numbers. Okay, so that's what you get when you unite the two. So that's just a pointer that I wanted to bring out at the end. But otherwise, this is the end of this tutorial. Thank you very much for watching. Please subscribe to our channel, like this video, share this video, and please stay safe and stay home. And yeah.